Hey, Thenuwan.
Hi, Zara.
Hey, we'll be going live in about 3 minutes.
Right, great.
Thenuwan, we're going live.
Right. Correct.
Modeling urban transport networks helps to better evaluate its performance and propose suitable traffic control measures. This session, conducted by Thenuwan Jayasinghe, will focus on how Python can be used to create and calibrate models and develop scenarios for a higher level of accuracy. Thenuwan is a commercial director at Boffin Institute of Data Science. His master's thesis was a part of Tom Create's Global Research Initiative. Please welcome Thenuwan to the stage for his session on how to automate traffic simulation models with Python. Thenuwan,
Thanks,
the floor
Sarah.
is yours.
Thank you. Thank you. Good evening, everyone. So I hope you are doing well today and as excited as I'm to be here. So as introduced by Sarah, my name is Thenuwan, and I work for Boffin Institute of Data Science, and also I work as a researcher in the field of traffic simulations. So I have been working with simulation models over the 5 years, and I was able to take part in some interesting research projects. So in this webinar, I'll be sharing my experience on how I have used Python programming language as a tool to automate certain processes in traffic simulation software. So we'll take one example in detail and go through. So, and also I would like to take a moment to express my gratitude to the organizing committee for giving me this opportunity. So without further delay, let's go to the presentation. Right. So the talk that I have is outlined in 3 steps. First, we will get a first understanding, or like a high level understanding on what traffic simulation models are. Then we will see why there's automation is needed in traffic simulation modeling. And then next we'll see how we can automate. So there we discuss one particular application using a commercial simulator. Right. So first, let's start with what. So what are these traffic simulation models, right? So what traffic simulation models ideally do is it simulate or mimic the behavior of movement of vehicles. Vehicles could be, public transport like trains, buses, or private vehicles like car, motorcycles, etc. And pedestrians, we all know, and the other entities such as traffic lights or pedestrian crossings, something like that, right? That interacts with the networks and the simulation environment. So those things within a transportation network, we simulate using traffic simulation models. So that is the idea. So the main idea is to closely represent the reality. So we all know that all models are not right? So we'd say that all models are wrong, but some are useful, right? So similar applies here. So, but as a modeler, our best aim should be to aim to represent the reality as close as possible. So this is a crucial step. Now, some of the use cases of traffic simulation models are, if you want to model existing systems, like if you want to say take Colombo, for example, and make a simulation model for like a Colombo, greater Colombo area, so the entire network, that is possible, so that you can see what are the traffic levels, what are the congestion, what is the network speed, etc. So that is modeling existing. And if you want to, on top of that model, if you want to estimate a future scenario, such as suppose as the population grows, or like a decline in population or change in urban structure, and then you have another set of, how people like movements, right? For example, we can capture their movements by using origin destination metrics. So these values will be changed time to time. So if you think that Colombo might have a increase in population, and if you want to predict in 2020 or 2030, how would be the traffic congestion look like, and if the traffic condition is too much painful, whether we should have another set of infrastructure or like other aspects like improvement of public transport, so transport demand side and supply side management. So these things can be tested. And other thing would be if anything that is very costly to implement in the real world, or like very difficult to implement. For example, a futuristic scenario could be a deployment of electric vehicles or autonomous vehicles or vehicle to vehicle communication, that kind of things. So if you want to model those, for those kinds of things also we use traffic simulation models. So there are a lot of use cases, right? So in terms of resolution of these traffic simulation models, we can divide them into three main classes. Now, the first one is we called as macroscopic simulation models. So what they do is they focus on overall flow and behavior of the traffic at an aggregated level. So it's ideally will be used for like modeling larger networks, where you don't need to model individual vehicles, but you model vehicle flows. And also if you want to model a public transport network of a city, then that case is also macroscopic simulation models are used, roughly speaking, right? And the other extreme of it is called microscopic traffic simulation models. So they offer the highest level of detail, where we model individual vehicles and their movements in a greater detail, right? So there are two extremes, right? And then we have another one in between. It is called mesoscopic level. So that is a bit more complex than macroscopic simulation models, but again, it's less complex than microscopic simulation models. Right, so our focus today is on macroscopic simulation models, but you will see when I get to the case study, you will understand it a little bit more. Right. So then the question comes, why we need to automate traffic simulation models, right? So that is a very valid question, right? So one thing that I see, the automation gives you efficiency, because if you want to create models in a fast-paced environment, right? This automation allows you for faster and efficient analysis, right? So that means you should be able to put your more time and effort on actual analysis rather than the model development, because it can become a tedious task sometimes, because you need to have your network ready, you need to have your other data such as travel demand that could be in different forms. Commonly, maybe you have heard something like origin destination matrices. So you have data in that format, and then so you need to assign this demand to the network and then have the model ready. So, but then again, if the network, some parts of the network changes or some part of the demand changes, then you have to start this process again. So if you have automated the process, then you can quickly adapt your model to the changes. And also similar to applicable when it comes to creating simulation outputs, right? And then maybe you do some further analysis or visualization. So entire pipeline can be automated, but of course you need some supervision just to check things are all right. But things can be automated to a great extent. That brings you efficiency. And then scalability. Maybe I have touched that a little, but if you want to change certain, if you want to apply the entire process to a new network, new demand set definition, something entirely different. But if you have, then you don't need to start from the scratch. Obviously, the network or the demand might be different, but you can directly use those previous methods that you have created and then apply it and then quickly create the model and later do some tweaks. But essentially, it will cut down a lot of time that you have spent on manual model building. Finally, one of the important thing is reproducibility, because now if you have automated a process compared to a manual process, then the manual process might be, once the modeler is changed, or like he or she left the organization or new replacement comes, then you would have to start things from scratch and again. But if you have automated flow, then it's possible to reproduce it. And also it's possible to reproduce your results, because if someone challenges your model or your model outputs, then obviously you can show the process what you have done and explain it. So there's a bit of transparency is also there. Obviously, of course, if there are errors, you can correct it. So it offers you transparency, and also you can reproduce at any to check anything that is there in your model and maybe cross check it. Right. So these three things, as I see, by automation, these three things can come. So now then we will look at a situation, an application on this application of traffic simulation models, right? So I'll be tackling a specific scenario. So I want to give you a small introduction on that specific scenario. So let's understand that scenario first. So I will have a small quiz on that. So past participants who are here, just tell me like which route you will be willing to take. I'll give you 3 choices and I'll explain each of them now. Right. So the first choice that we would have is, the scenario is like this, sorry. So you are at home and you are suppose you are daily commuting to your office. So this is where your office is at. So from your home to office on the morning, you have 3 options. Now, option number 1 is the green route, where you have to walk for 10 minutes and then you have to wait at a bus stop for 5 minutes, and the bus appears, and then you have to take a bus trip for 30 minutes and then alight at a stop, and then you will have to walk for another 10 minutes to reach your office. So this is option number 1. We can call it as the green route, right? The option number 2 is you have to walk 5 minutes Now you go to a train station, the frequency is high. So on average, in 2 minutes, you can catch a train. So you have to wait on average 2 minutes. And a train comes on 15, you have to take a 15-minute train ride, and you have to alight, but you have to transfer now. So this transfer stop is a bit large, so you have to walk and wait altogether for like 8 minutes you have to spend. Then the next train comes, another 15-minute ride, so you get a light, and you have to walk for 5 minutes to reach your office. That is option number 2, the purple line. The third option is where you have to walk 5 minutes and then wait for 2 minutes to get the bus. And this is a slow bus, but you have to like travel like 60 minutes. And then you alight and then walk for another 5 minutes. So that is the red route that you can take. So these 3 options are available. Now, the underlying assumption on my question is all 3 in terms of cost or the travel, the price or the tickets, these 3 routes cost equally for you, right? And of course, you can't take Pick Me or Uber, your own vehicle, no. But these are the 3 options that are available for you. So my question to you is which route that you're going to take. So you can answer. You can go to this, can scan this QR code and go to menti.com and start voting. Actually, the voting is has started now. So I'll keep this slide for like 10-15 seconds, and I will show you back the choices that you have. Right. Anyone? Okay. Some are already in, so I'll show you the choices. That's again the green route, the purple route, and the red route. Right. Others who want to join, I'll show this again. Right. Right. So maybe not much are there, but yeah, let's, okay. So we'll take another 30 to, for 1 minute or 30 seconds, and then we'll see. Right. Okay, so these are the choices again you have. Right. I will start a countdown. So maybe we'll take 30 seconds and then close the poll. Right. So maybe we have to satisfy with 3 answers, but yeah. All right. So thanks for the votes. So let's say most of you out of 3 that has responded, most of you take the green route and one of you will take the purple route. Right, great. So no one is taking red route. Let's see what, okay. So now if you take the travel time that you would have to spend on these routes, it's like this. So the green route, there are, right. So on the green route, you spend the time that you spent on walking is called access and egress, right? So access is the amount of time that you walk towards the stop from home, and egress is from the last stop to your destination. So 20 minutes you spent on walking on green route, transfers 5 minutes, in vehicle 30 minutes, roll together 55 minutes. And then on purple route, your access egress is 10 minutes, your transfers waiting 30 minutes in vehicle, so altogether 50 minutes travel time. So similarly on the red route, you spent 72 minutes. So if I, so yeah, so most of, I mean, out of these choices, so 2 of you have chosen the green route. So, but it's in terms of travel time, it's still sort of longer than the purple route, right? So these choices that people make is different. So the ideal situation is that you're not only making your choices just considering the travel time, like the clock time, but actually you make these choices by using something called a perceived journey time. Now this is the concept, and this is where we get into simulation and sort of go a bit deeper into this topic. Now perceived journey time is because that passengers actually perceive the different components of your travel differently, right? Different from the actual time that you spend, right? So then it says that the underlying assumption is that passengers make their travel decisions based on the perceived journey time and not based on the actual time spent on the network, right? So now if you put a perceived journey time to an equation, it will, you can calculate it something like this. So I'll explain these components. So PJT stands for the total, like the perceived journey time. So it could be minutes, hours, or like a time value. Now the first component is the in-vehicle time, right? The time that you spent on the vehicle, and you multiply it by a certain coefficient. So if it's 1, so that means the perceived in-vehicle time and actual in-vehicle time is the same. So similarly, you have components like access time, that is the initial walking stretch. And then you have the origin wait time, that you wait at a bus stop for certain minutes or just for the bus arrival. And the walk time, the transfers, in between the transfers, you have to walk. So that is also, you have to multiply it by another wait. So, and then transfer wait time, right? And then the egress time, that is the last leg, last walk that you do. And then based on how many number of transfers that you do, you add a penalty. Now suppose you do 2 transfers and the penalty for that is 5 minutes. That means your perceived journey time increases by 10 minutes. So it all adds up, and then a final perceived journey time is calculated. So it is, in the modeling, it is assumed that you make your choice, the route choice, based on this perceived journey time, right? So now the problem in simulation modeling is that now simulations have default values for these C components, right? These coefficients, you have default values, right? But from network to network, city to city, these coefficients might be different. right? Now, for example, if you take Colombo and equally with a country like Singapore, if you compare them, the time that you spent on a bus stop in Sri Lanka and also in Singapore, you might feel it differently, right? Because the infrastructure is different, thereby you perceive the time that you spent on a transfer is perceived differently. So in Sri Lanka, most likely you will try to avoid transfers as much as possible, right? Because it adds adds to a perceived journey time a lot, right? So then the problem is, how do you find these numbers, right? So how do you find these appropriate numbers? Now, one way is that you can do a survey. You completely forget simulations, you do surveys, and then you do some statistical test and find it. But if you have data about the passenger movements on a public transport network, then you can use simulation based methods to find these coefficients. And that is where we use certain techniques, and that is where we use Python with a simulator and get its support to get this done, right? So this is the problem that we have. Okay. Now, now to the way of finding this is something called model calibration, right? So model calibration, we say it as a process of adjusting models parameters so that the model can be in close representation in the reality, with the reality, right? So that is for any model calibration, right? So if you take a typical machine learning project, like if you do a training phase of your machine learning model, like you take a linear regression and then fit it to your training data, then you underlying you tweak some parameters, right? So that is, I mean, it's like a training phase. So you train based on the actual data that you have, right? So similarly, model calibration, we can somewhat equate to that. So that is applicable for any calibration. Now, the transit route model calibration is the specific problem that we are looking at, has some inherent characteristics. Now, these interactions between the model parameters and simulation outputs are very complex, because if you take a bus, it has a capacity, and so some buses may have 60 passengers, so not all the passengers can go on one bus, right? So the route choice is also based on the capacity of the vehicle and the headway of the vehicle, and probably the conditions of the vehicle, right? Some might prefer trains over the buses or vice versa, right? So these so some additional complexities there, therefore you cannot solve it using an analytical form, and that is why exactly you need simulation based methods to find this, right? So then we consider, because we cannot solve it as an analytically solvable form, we consider this as an optimization problem, and our objective is to minimize a certain error term. So we can define an error term and we try to minimize it based on the simulation outputs and also using the corresponding actual values, right? So so the actual values could be like, if you stick to this passenger transportation, then that could be on a given bus route, what is the passenger flow for a given day, an aggregated measure, right? So it's better to have, when you collect the data, it's better to collect them as a big disaggregate level as much as possible. But when you then into modeling, you can aggregate as any way you like. So, but they have to be like in the same scale, right? So it has to be like an apple to apple comparison, the simulated and observed values, right? Okay, so the constraints that we have in this kind of problem is that, so we assume, or like we fix, because we don't want to increase the dimensions of this problem. That is one reason. And also we fix in-vehicle time as 1. The coefficient of in-vehicle time, we set it to 1. Partly because 2 reasons. Of course, we can reduce one dimension from our optimization problem. And the other thing is that we can now interpret our results. So we can say if the walk time coefficient is 2.5, then we can interpret the result saying that compared to in-vehicle time, passengers perceive the walk time 2.5 times more, right? So your results are also interpretable now. So that is another advantage. And then obviously we assume that the wait time and walk time coefficients are greater than 1. So thereby we can cut down certain solutions in the solution space, right? That will help us to the calibration algorithm that we'll later discuss to navigate through its space in a better manner, right? And also the simulator itself has constraints, like the simulator accepts certain value ranges. So you have to respect those boundaries, and our values should be within those upper and lower thresholds. So in terms of constraints, those are like basic ones that we have used, but of course you can add more, right? So some can be able to say wait time coefficient should be greater than walk time coefficient, right? So then you can again have some logics and restrict the solution space, right? Now how we can solve this next book. So we know the problem. Now we need to know. So our problem is actually find those coefficients, and we use a method called calibration. Now how we can do the calibration? So there are 3 ways to solve it, in my opinion, right? So the first one is trial and error, right? You take, you assume certain numbers, you plug it to the simulation, you run the simulation, you take the simulation outputs, you compare it with the actual values, you calculate an error. Okay, you then think that, okay, error is too much, I need to take these numbers, and then you manually adjust them, you run it again, do this, you keep doing it until you get satisfactory result, right? So this is largely dependent on the modeler's experience, right? And this is very tedious and it's hard to replicate. If someone asks you, how did you do it? Obviously you cannot explain how, because it's a thought process. You make judgment, a lot of judgmental call to find the optimum numbers. And this may stop at a local minima because you don't check the entire solution space. You just hand pick certain values, and then you might accidentally trap at a minima, and then you thought that, okay, this is the correct value set. Okay, that's fine. This model is calibrated. Right. So the other method is brute force approach. You take all the possible combinations in the solution space. You using a program, you plug those values, run the simulation, and get the results for all the pairs, right? Now, if you want this coefficients into like 2 decimal accuracy, you like, lot of the solution space is very large. You have a lot of numbers to, check using this brute force approach. Now, this is computationally very expensive because these large models, if you take an example like a city scale model, would take, if using some good performance computational infrastructure, if you use, may at least take 30 minutes to 1 hour to run a single simulation run. So it's computationally very expensive, and probably you won't be able to finish calibrating model during your lifetime, and it will need a couple of generation of time to calibrate the model. So that method is also out. The most, or the third and the best method that is available for us is to use algorithm based optimization technique, right? So that's automated, has higher accuracy, and it's less computation expensive, and it's efficient, scalable, and reproducible, right? So those are the advantages. So let's now go into how to do this, right? So if you take an algorithm based approach, you start, you have your initial conditions, you plug those in, those coefficients, let's say initial coefficients, you plug into the simulation, you run the simulation. So in order to run the simulation, you need to have your network and also the origin destination metrics also you need. That is where the travel demand comes from. So from that, you get simulated outputs, and you'll also have, for that particular simulated output, the exact matching ground truth you have captured, right? This is a must, right? If you have poor data, the calibration is wrong. It's like garbage in, garbage out, right? So if you have ground truth, then you can calculate an error term, right? Could be any error term. Maybe there are different choices. So calculate an error term. And if you see whether that error is minimum a certain threshold, right? So there are certain acceptable thresholds. So if that is less than that threshold, you stop the process. If not, you send it to a calibration algorithm. In this case, we used a calibration algorithm called SPSA, simultaneous perturbation stochastic approximation, because it's very less expensive to run for like this, because this objective function evaluation is very costly to implement. So you want to reduce the number of simulation runs as much as possible. So SPSA works best for that kind of concern. If anyone is interested, I can obviously talk more on that algorithm. Right. So then this calibration algorithms gives you a new set of estimates. You plug those, rerun the model, evaluate the objective function, and you go through this step until you get a certain level of accuracy, right? So in terms of objective function, you can we use something like called RMSN, root mean squared normalized error. So here yi is the observed values, yi hat is the simulated value. So that's any error term that you can use, but choosing error terms, there's an art and science behind it. So then let's talk about the simulator. Right, so the simulator is called PTV Visum. It's a commercial simulator, so it's a licensed product. There are open source simulators as well. That's why I highlighted that difference. So it's a macroscopic simulation model, so that you can use for like aggregate demand modeling. Like in our case, if you want to model a public transport network, this is an ideal choice. So yeah, so transport networks. And for public transport planning, this is heavily used, right? And also you can use it to develop transport strategies and check different scenarios and come to idea. But our main idea behind today's talk is on public transport planning, right? Okay. So now how we can couple the simulator with Python? That is the next question, right? So we have Visum on one side. We have Python on the other side. Now the Visum provides you a Visum.com API, right? Where you can use to communicate between these two, right? So any values that you generate through Python, you can pass it to Visum and run the simulation. And at the same time, any simulation outputs that you get from the simulator, you can retrieve through this API, right? So you can start communicating, right? So if you go back to the step, previous calibration step, so your simulator now becomes PTV Visum. Simulation outputs you can get from API, and the objective function evaluation part, this part you can do the error calculation and everything you can done inside Python. The convergence check also you can do with Python, and the calibration algorithm execution part is also done in Python. And it spits out new set of estimate, and that is sent to the simulator back through the API, and then you run it again until you reach a satisfactory convergence. So normally what we do is we fix number of iterations, because this is very computationally expensive to run, and then you know by 2 days, 3 days this has run, and you get the results out, right? So then you check it, and if you want, you restart it and do this multiple times, right? Okay, so this is what you do. So basically this is inside Visum. These are the values that you need to change, like in vehicle time, access time, egress, walk, origin wait time, transfer wait time. Those are the values. So out of this, you don't need to select everything, because you can choose the parameters that you want to calibrate, because for example, you can fix in vehicle time as one. But ideally what you do is these new estimates that is sent through the calibration algorithm is passed to these slots, and you execute the simulation. That is what you do ideally, right? So now to do this using Python, you need a couple of things. And now the first thing is you need to load Visum we call it a version file, right? The Visum file, the network and the data is all, of course, everything is there. So you need to load it into a Python environment. So the API supports that. Then though there are a lot of things involved, but I'm just showing two like good, I mean, easy to explain, or like easy to like which suits the context kind of two things. Now the first thing is you need to load it. Then once you have that, any values that you get, you can retrieve, and also you can set them back. Now, for example, this, what we do here is, now this estimates list that you could have probably taken from the simulation algorithm, right? So the calibration algorithm. So calibration algorithm spits out new, let's say, 3 values. So this should be like 0, 1, 2. Yeah, I'm getting it like a list, and then I get the corresponding value from the list, and I set that value, right? So you basically this impedance parameter object, this what you get here is the actually, that is the that from there you can access these values, or like you can set these values, right? So basically then you can it has a method to set attribute value, so you can set those values accordingly. So these are standard names like walk time value, origin wait time value, and transfer time value. So those things you can set, and then once you set that, you can run the simulation again. So once you run the simulation, there should be another function to output the data and maybe transform it in a pandas data frame or something, and send back to Python for the error calculation, right? So this is how the setup works. So ideally speaking, this is the entire setup. I just show 2 parts of it, how to load it and how to set values. This part and the initial loading, right? Right. So let's discuss the case study, right? So the case study that we did this entire thing is for Singapore public transport model calibration, right? We wanted to calibrate Singapore public transport model based using this method, right? So now if you take have a look, this is as of 2000, I think the data was collected 2013 or somewhere. Yeah. So back then they had 4 MRT lines, 4 LRT lines, light rail transit lines, MRT for mass rapid transit, and they had over 300 bus lines. These are normal bus lines, right? There are express bus lines and special bus lines for holidays. We are not taking those. We are taking the average, let's say a Tuesday, Wednesday, Thursday kind of travel behavior, right? Because that represents the normality. And then in terms of models, so you know that in Singapore, you can you have a smart card where when you get into a bus or train or whatever, you tap it, and then when you alight or like get down from a station, you tap out, right? So that means the origin of the bus or the public transport and the destination is captured, or transfers also captured, because when you transfer through a particular gates, you need to touch the card. So this starting point, ending point, and certain midpoints are captured, right? So from that, then also, you know, based on the number, based on the step, you know which bus that you got into, or like which train line that you got into. A bit tricky, but possible. And the time that you got into, like these kind of other data, like a metadata also is collected. So then you can, using that data itself, you can calculate, okay, on let's say bus number 100 or 101, let's say there's a bus number like that, on a day, how many passengers have traveled on that bus. So that if you put those smart card data directly to the simulator, that is called direct assignment. You cannot run simulations on it, but you can display it, sort of show you what's the current situation is, right? But you can't do any changes. So this is called direct assignment. So from direct assignment, you can get the ground truth or the actual values, right? That is from smart card. Yeah. Now, when it comes to simulation model, I told you that we had origins and destinations. So from that, we can create an OD matrix. For each stop, we consider as an origin and also a destination. So if you consider that, you have 4,886 origins and destinations. So this will give you 4,886 by 4,886 OD matrix, right? So this you plug into the simulator as the demand, and you run that demand on this network by changing those coefficients that I showed you earlier, right? These coefficients that we set, you change them, you run it, right? So that is the idea. So we did that. That was actually my master thesis project. So this is the results that we got, right? So you got results. These are the default values of the simulator. This IVT is for in-vehicle time, OWT origin wait time. This is transfer walk time, transfer wait time, transfer penalty. So we considered all these values. And using a first variant of our calibration algorithm, we ran it for 80 iterations. And we got, at one variant, we got our best estimate at 79th iteration. In the second variant, we got it at 76th iteration. And based on the best values that we got from here, we use the best values that you found as initial guesses, and we restarted the algorithm for another 20 iterations, right? So after doing that, because this algorithm has a learning rate, so as the number of iterations increase, the learning rate sort of decreases, and the ability to navigate through the search space diminishes. So therefore, we restarted it. So once we restarted it, we get a better calibrated values. Now, these are the calibrated values. Now, how do I know that these calibrated values are the best values that I have? So for that, we can do some validation tests. Now, this is how the error reduction happened. So this is for the passenger trips on transit line routes. So so this is the red line is for 0 transfers, that is like direct trips. Green line is for 1 transfer, 2 transfers. So these errors in this plot, x-axis is the iteration and y-axis is RMSN, but that is scaled, right? So the error doesn't go to 0, but just to show it on single plot, all these like sort of min max sort of normalized and showing it, right? So don't take it wrong that the error is completely reduced. It's very hard to do it, right? But you see the error is reducing, right? So that is what I wanted to show. And then you can do the similar to passenger transfers at stop. So if you take the total transfers, particular transfer, the total errors, the transfers in terms of error, that error is also we are reducing through this using this calibration algorithm. And finally, if you take a particular a transit mode, for example, bus, now the red plot on the left hand side show you before calibration how it looks like. So even the the default values of the simulator gives you a good fit, right? You see that R squared of like 91%, but the calibration can you make even better, right? So if you see this, if the calibration is ideal, the observed value and the simulated value should be the same, right? So that means you need to have all your points on this 45-degree line. So that denotes, so in the initial setting, the intercept was like minus somewhere around 2000, right? But once the calibration is done, the intercept value is reduced, right? So that tells you that the calibration is good, and also the R squared value is slightly increased, right? So so this is for this is not for buses. This is for MRT and LRT lines. So these 4 dots are for MRT lines. These others are for LRT lines. Sorry. So again, you can see it's a slight increase, but that you can get only through a calibration setup like this. Manually, it's possible to reach this, right? Right. So in summarize, if I summarize my content, so we estimated perceived journey time parameters. So from this study, what we got was the passengers in Singapore perceive the transfer work time 3.6 times more than the in-vehicle time, right? That is from this study, that is the results. And also the passengers, because transfer work time, if I interpret it, maybe it's a warm country, so you don't like to sweat too much, so you don't want to spend too much time on transfers, and probably this might perceive more. So that is the explanation, but simulation, it's a different result that we got, but we can try to explain it using some other context, if you know the context about the country. Now, the passenger perception of wait time at transit stops are almost same, and it's closer to 1. So it's closer to in-vehicle time coefficient. So that suggests that somewhat suggests that there are conditions, or like their infrastructure is get better, so that passengers don't feel it too much. It's like a seamless sort of a journey that they experience. So that is one thing. And the mean perceived journey time for a transit trip in Singapore is like 44 minutes. So you see how good that network performance is, right? So in average, in 45 minutes, you can go to the origin and destination. Right. So in conclusion, this is my conclusion. So automation of traffic simulation models gives you efficiency and scalability and reproducibility, because all the things that I mentioned earlier is very efficient way to run. It's scalable and it's easily reproducible, right? So yeah, so that is the end of my talk. Actually, before ending, I need to acknowledge certain partners behind the case study that I work with. So TUM Create Singapore, and my supervisors, Dr. Andreas Rao, Professor Costas, Dr. Sain, and Moid. So I need to like acknowledge it, because without their support and help, I couldn't have done this. Right. So that's the end of my talk. So I think I am on time. So I'm okay for any questions that you may have.
Thanks, Thenuwan. Yeah, please do drop your questions into the Q&A box at the bottom if you do have any. In the meantime, thank you so much, Thenuwan. In that session, I'm pretty sure we all learned how accurate transport models can be developed with Python. We've all had a series now of fantastic talks from so many learned individuals, and we'll be wrapping up soon with something I'm pretty sure you guys are going to find exciting. Please join us now for our final keynote, Python's role in unlocking the secrets of the universe with the James Webb Space Telescope. Thank you once again, Thenuwan, and we'll see everyone back on the main track.
All right, thanks.